Ready.
This chair's over there. Oh, I'm not coming on.
Okay, we're all set.
Okay. All right, so I wanted to, if there's time at the end, I want to give this little speech about the threefold way in math. So if anybody wants to hear that full speech, this is one of the threefold ways. Okay, so I started drawing a bunch of dots on the board. See the dots? Yeah. Anybody, and then I went dot, dot, dot. I got tired of drawing, okay? Can anyone see a pattern in these dots? Or raise your hand if you see a pattern. No, not you, Austin. You all are mostly undergraduates, right? Okay. Austin's a grad student. Mike can answer my questions. He knows the answer. Does anybody else see a pattern in these dots? Yeah.
The edges are strangely shaped, but it appears they're all equidistant from each other.
Yeah, yeah, there's something, these are, I meant all these distances to be equal and all the angles to be right angles. Okay. So, does that answer your question? Okay, they're not, this is 1 and this is 1, so this is square root of 2, right? So, bunch of factors, right? Anybody see a pattern? No, not you. We talked here before. Okay. Anybody? Oh yeah.
You can shift the entire thing 1 unit to the right and you get the same.
Say it again.
You can shift the entire thing 1 unit to the right and you get the same looking image.
Yeah, yeah. If you shift this to the right, you get the same thing. Shift it to the left, or you shift it up, or you shift it down. And you can keep shifting. If you did it infinitely far in all directions, you could have this symmetry, right?
Yeah.
So, and the symmetries of something can be composed to give other symmetries. They have inverses, so they form a group. Raise your hand if you've heard the word group in a mathematical context. Raise it up so I can see. You're not raising yours? Okay. So you've all heard the word, not all of you have heard the word group in a math context. Oh, you're raising like this? You're raising like this? Okay. So everyone basically, okay. Yeah, so this is an example of a picture of the elements of a group, actually, because if you take any point and you want to have take any other point, like way over here, you just shift this over 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you shift it up 1, 2, 3, 4, 5. You get to that point, right? So this is sort of a picture of a certain group of symmetries of the picture. A certain group of symmetries, right? And the translation's this way and the translation's this way. Does anyone know how to write that group in notation?
Yeah, I guess this isn't the answer you're looking for, but aren't there also...
If I can't read your lips, I can't hear very well. So.
Yeah. Aren't there also rotational symmetries? Like
There are some, yeah. There's some. There's more symmetries. That's true. So there is a rotational symmetry by 90 degrees. So in fact, I'm lying. I often lie. Austin to tell you that. I mean, I don't. But I'm interested in kind of, but that's a finite group. In other words, the symmetries of the square rotating, and you also have some reflections. They form a finite set of symmetries. But I'm interested in infinite groups. So this doesn't change things too much. Like 2 times infinity is still infinity, so to speak. So I'm interested in infinite ones. So if you sort of think that you have horizontal shifting and vertical shifting. You know, you can do any number of horizontals, any number of verticals in either direction, and then you get a lot of expressions. And notice that if you shift horizontally by one and then shift vertically by one, and then that's the same as shifting vertically first and then shifting horizontally. That's the same. So these two symmetries commute. You do, doesn't matter the order, right? Now if you just did one of them, V, 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 you just count the number, and that's an integer. Shifting to the right, say the positive integer, shifting to the left, you think that's a negative integer. And then, you know, the exponents add, right? This is like V to the fifth, V, V, V. This is like V cubed, and then this whole thing is V, first do V to the fifth, then do V cubed, so this is V to the eighth. Right, so you're just really adding the exponents. So this group is like the group of integers, positive and negative integers. And then you have another positive and negative integers going this way. So the symmetries of this figure is more or less, except for the examples of the finite symmetries, which I want to ignore. I even forgot about them. Or at least these symmetries are, they form a group which usually we denote the integers like that. Is that how people make Z's? That's how we
usually
make
like
Z's,
put
right?
the slash, like the additional slash on the diagonal. Blackboard.
Well, you don't put this little thing here?
No.
Huh?
Yeah. Some people do. It's like there's a blackboard.
Oh, just like this, right.
And then there's another slash on the diagonal.
I don't know why. Okay, so, and then since you really have two Z's here, whoops. I don't know why I want, I lived in France 20 years, and so sevens, you put a little thing. That's what my brain is doing. Okay. And then this is kind of a commuting product of these two Z's, so you usually write this like this. One notation. Okay. Okay. Now, one more thing. This is related to a picture. There's sort of you can sort of. This is like a region which is called a fundamental domain. You can draw the, no, that didn't come out very well. You can sort of complete this picture like this, and then you can think of tiling the entire, there's a chair over there, or there's one over there too, so. You want to walk in front. You can have one of these chairs. You want to sit here in the middle? I usually sit in the middle, so I can ask questions. So you can sort of complete this picture, keep going like this, and then these tiles just shift together. So it's a symmetry of the tiling, like on the, well, not quite, well, really almost the same. Actually, this. So now we can take these dots and think of having pieces of paper here and glue them all together, and we get an infinite surface, right? And this has this symmetry group, translating this way and translating this way. And then you can identify, I mean, suppose you take this, you can sort of, let's glue a point to the translated point. Like if we do it vertically, what would you get? Suppose we just glued every point to its various translates vertically. So we do that. But we could think of that like this. Just take one strip here and then just glue this side to this side. Just goes on forever. And just glue that side to that side. And what would you get? You did that. Take a piece of paper, infinitely long, this infinitely long strip, like a long computer tape. You probably don't know what that means. When computers first came out, there were these tapes. Anyway, and then you glue this side to this side, because I want to identify every point to its vertical translation. And what would you get?
A cylinder?
Cylinder, right, because a cylinder like this, and it would keep going. Right, an infinite cylinder. Okay. Now I've gotten rid of one of the z's. Say, let's say that. So let's say I have the vertical one here and the horizontal one here. So I've identified out one of the z's. Now I want to identify. Now I want to do the same thing with the horizontal translation. Well, the horizontal translation I could think of as, see, all these strips become cylinders of unit length when you do this together. And so you have and then now I can identify under the horizontal translation. I identify a point to all of its horizontal images. Just do it and then form that object. Well, here's a picture of the square. I folded this part to this part, and I get this cylinder here. That's a piece in the middle. Now I want to glue this to this, okay, by translation. Well, you can actually do it as a topology. You take this out, you stretch it, turn it around like that, and just glue it on. And then you get, where's the pizza? Then you get a bagel, right? Get this, okay? So you sort of, these is, if I open this up like it, I cut the bagel and maybe stretch it around and get this cylinder. Okay. Some of you are nodding. So this is this process where you, so you could go backwards. You could take this thing and think of it as a roll, like, you know, how people paint with paint brushes. Well, not paint, what do they call them? Paint rollers, right? The tape. You just put it down and you push it. And it's a cylinder and it rolls out a little strip of paint. You just keep going like that, right? You get this whole infinite strip of paint, right? So you could think that if I took this infinitely long paintbrush and put it down here and rolled it this way and then rolled it that way, I would paint the whole infinite thing, right? Okay. So we call this the covering space. This is this infinite flat plane wraps around and covers this infinite cylinder. Covers it. If you take a small picture here, you can repeat it on the cylinder and then you roll it out, but this is like on the paintbrush, and then it rolls out and it becomes in all these places. So this part here just gets repeated over and over again in this direction. So you're just unrolling this cylinder. Well, then we can think of this infinite cylinder as a covering space of this torus. We just take it and wrap it around, wrap it around, wrap it around, wrap it around. what's kind of interesting is that up here, so now, this was a great discovery of Riemann and Poincaré. In the 1800s. He did examples and he abstracted what the examples meant. And this thing is called the Riemann surface, and this picture I've been describing is called the universal covering space of that Riemann surface. And this group of symmetries of the universal covering space is called the fundamental group of curves on this torus. Well, whether or not those words have you've heard before or not, it's not important now. But that's just, you can remember them, write them down, look them up later, learn them later. But this is the picture. You don't need those words to talk about this picture. Okay? Okay, now let's get to another example. So you could draw, now I want to talk about, so let me leave this group, this mathematical group. It's called C plus. This, by the way, this has a name. It's called the free commutative group. And Abel, a Norwegian mathematician who died at age 27, tuberculosis. Riemann died at age 39 of tuberculosis. Used to be every 2/3 of the not natural deaths were by tuberculosis, even when I was 5 years old. Anyway, this is called the free abelian group on two generators, V and H. Two generators. Abelian means they commute. V composed with W is equal to H. Okay. Now this picture is a little bit more mysterious. Now I want to do the opposite. I want to say VW does not equal WV. In fact, I don't want to have any such relations between V and W, between two generators. Let me call them X and Y now. No, I don't know what to call them. U and V. No. A, B. S and T. ST is not equal to TS. You do T and then do S. It's not the same as doing S and T. A good example is Superman. You know, we have our underwear and our long pants. There's an order that you usually put them on. You put your underpants first and then you put your long pants. But you put them the other order, you can do it. Put your long pants on, then put your underpants on. Then you look like Superman. Right? Does anybody know who's Superman still? Does he still exist? Okay. Anyway, that's not commutative. They don't commute, those two operations, putting on your long pants or your short pants. Okay? So, but I don't want anything to commute. So it means I don't want even the inverses to commute. So I'm at a point, and I've got two operations, S, and I have S inverse too. I'll call it S bar. I have the inverse. I could translate this way and translate that way over there. I have +1 and -1. And then I also have another operation t, and then t inverse, and then again I get here. Now, I don't want to do t inverse because I'll just go back to there. I want to go out, so I could do s and s bar, and I could do t again. So there are really 4 choices because you have t and t inverse, and you have s and s inverse. And if you're at any one point, suppose you've done something and created a new point by applying these letters, this last point is either one of these 4. So I don't want to use the inverse of that one, whatever it was. So I have 3, because then I would go back here. I want to go on. Because you just do, put your pants on and then take your pants off and back where you started from. So I'm not doing anything. Okay, I don't want to do that. I don't want to backtrack. Okay. So I have 3 choices to go. Because the last choice, I don't want to do the inverse. I don't want to backtrack. I want to do something new. I don't want to do the inverse of what I just did. So I have 3 choices. So I start drawing a picture of that. So I start here, and I have 4 ways to start. I have sort of the identity element of the group, you might say, not moving anything. Now I have use S or S inverse, T or T inverse. And at each of these points, okay, now to get to one of these 4 points, I did, let's say I'm here, I did something to get here. I don't want to do the inverse of that, so I have 3 choices. So I go dun, dun, dun. And then I get to here, and I have 3 more choices. So now I have to keep doing this, and now you see, it's hard to draw this picture. Because every time you do a layer, so if you're counting words, you know, this inverse stuff is sort of silly. You just think you have 4 letters, and they're related by inverse, and then you start out and you have, so how many points do I get here? I've done this 1, 2, 3. So these are all of the 3-letter words in these 4 symbols without any backtracking. What?
36. 36.
No, tell me the reasoning in your head.
Oh, there's 4 ways you can start off, and after that, you have I think two stages, and each stage gets you 3, and so that's 4 times 3 times 3 equals 36.
Okay, yeah. So he's saying the first stage there are 4 choices. The next stage you have 3 choices at each of those, and the next stage you have 3 choices at each of those. Right. So he did it in his head. 36. Okay. So if you keep going, so you get 4 times 3 to the 6. Anyway, this is starting to be a big number. Anybody know this number? Anybody compute it?
About
2908.
81, 2, 43. 29. Times 4. 2800.
2906.
76. I don't know. So something. Anyway, this is what they call, see, oh yeah, let's go back here. Let's count how many points here. Now, here it's more tricky. If you write down an arbitrary word and V and H, see, VH, VV, HH, VV, something like that. And you have H inverse 2s, but that's the -1. But anyway, you sort of have to add up the number of V's and add up the number of H's because you can move them across each other because they commute. Right, so it's just roughly the sum of the exponents on the V's plus the sum of the exponents on the H's. So if I take the word length to be like a distance, and I go out a distance r, how many do I get? Suppose I go out a distance 100, say. How many do I get approximately? Somebody's laughing right there.
You get 2 to the 99.
Are you guys with it? Are you understanding? So if I go out 100, so that's like that's why I tried to draw the dots this way. I wanted to sort of look like kind of a circle. So I'm imagining going out a certain distance. Okay, or the distance is the distance in the blackboard. So how many dots do I get? Approximately.
100 squared.
Remember the formula pi r squared? That's the area, right? The circle radius r. Okay, so pi is 3.5 or something.
Oh, this is like
Three,
these Putnam questions. How many
What?
integers are in the circle, radius, whatever? How many coordinate points?
Right. Yeah. So, but roughly the area. See, you could sort of say how many squares. So each square has area 1, and out here some of the squares are in, and these are in, and then this next one is out. But anyway, there's some error term around here. But roughly, the squares that are inside, if this is really a big disk, okay, it's roughly the area plus some error term, which is like a strip around the boundary. But the strip around the boundary is 2 pi r. Is that the right formula for the circumference of a circle? So it's sort of like r. Forget the 2 pi and the pi. When we want r, a million squared is really big compared to a million. Okay, so I'm working. I want to get a gross picture here. So the answer is, if you take all the words out to a distance of million, roughly it's a million squared. Is there a name for that?
Trillion.
Trillion. Oh, do you work in finance? No?
I just billion.
1,000 millions, a billion, 1,000 millions, a trillion. Okay. Yeah. So here there's a big. So here it's like you go out a distance of 1 million. You've got to put these 3's together 1 million times. It's much bigger. Right? It's like 3 to the million. Right? Which is much bigger than a million squared. Right? So what is this group even? So this is, and then it turns out if you could imagine this abstractly, it really looks like locally like Manhattan, except there are no blocks. In fact, the way I usually draw this is like Manhattan. It's like Manhattan, but you can't go around the block. There's no relation. See, if you go around the block, that means there's some word that gets you back to where you started with. And I said there's no relation among the operations. So this is again a group, and this is, well, the math notation is this. Put this star there. It means it's like a free non-abelian group generated by 2 generators. And it's different from that group because the number of words of a certain length is growing exponentially with the length. And there it's just going like a quadratic polynomial. So they're very different. Okay, and you can see it from the pictures. If I can't draw this, I can't keep all the lengths. To draw this on the blackboard, I can't do it unless I make things small here. Now I want to draw it like everything is equal size. Okay. So the first idea is, which made me very happy when I learned it, is that you know, so groups are like, they have generators, you know, G10 or something. These are different generators. You have their inverses. And then you think of these as abstract operations on something, and then you can think of them as like symmetries. This is how they, but this kind of was invented by Galois. Anybody heard of Galois? So, and he died at 20. Actually, he wasn't quite 20. He did a duel, lost. It was very political in France then. Believe all that. Anyway, just looking at algebraic equations, and there was symmetry in the algebraic structure. These are called Galois groups today. They were all finite groups in his time. Anyway, so that sort of started the idea of operations that are symmetries of some structure, and they compose them, and you know, there's this wonderful law called the associative law. If you know, when you dress, you could put on, I keep referring to this dress thing, you could put on these parts, and then that, you know, so groups are like, they have generators, you know, G10 or something. These are different generators. You have their inverses. And then you think of these as abstract operations on something, and then you can think of them as like symmetries. This is how they, but this kind of was invented by Galois. Anybody heard of Galois? So, and he died at 20. Actually, he wasn't quite 20. He did a duel, lost. It was very political in France then. Believe all that. Anyway, just looking at algebraic equations, and there was symmetry in the algebraic structure. These are called Galois groups today. They were all finite groups in his time. Anyway, so that sort of started the idea of operations that are symmetries of some structure, and they compose them, and you know, there's this wonderful law called the associative law. If you know, when you dress, you could put on, I keep referring to this dress thing, you could put on these parts and then put this part on. You do it in the right order. But it doesn't matter, I've got two parts to put on down here, and one part up here. I could do these two first and then put this one on, or I could do the first one here and then this one, sorry. No, first I do this, and then I do, the associative law. I'm trying to explain the associative law, and I'm not doing it, right? Anyway, operations, it's so banal that you can't even say it. It's just operations form the associative law. You can do them when you write, that's why when I write the word down, I don't put any parentheses. See, there are certain things that don't associate. So you could do this and then do this, and you could do this and then do this. And sometimes these are not equal, but in groups of symmetries, they are equal. So when you define a group abstractly, you have to write the associative law, write the inverses, and then you have the notion of a group. You have an identity element, something like that. Okay. So these are very important in a lot of parts of math and physics. In fact, symmetry and locality are like the two principles of most physics. Okay. So when I first started learning math, the groups were presented like this. You give the generators, and then you give like maybe G1 commutes with G10. These are called relations. You give more relations. You don't have to give this relation because this is part of the definitions. And then you can form the group of all words, this construction is a little bit non-trivial. You first form the free group generated by these things, and then you introduce an equivalence relation that says, like, this word equals this word. And if you multiply this by the same word, same thing on each side, this is also a relation. So you have to keep doing that. That's where this comes in a little bit. And then you take, this is the thing that we have in math that doesn't exist in any other science. We have structures on sets. So here the set is just a set of words and these symbols. And then there's an equivalence relation on this set, and we can form the equivalence classes, various subsets that are equivalent, and then we can form the set of equivalence classes. And that has the structure of a group, because you add all the consequences of this relation. So when you give a bunch of generators and give some relations, you always get a group if you take all the full consequences of all the relations. So that's a pretty unwieldy object. If you, it's very complicated because you have all these words. So I wasn't going to work on group theory. But then a mathematician named Gromov came along and said, well, let's make a picture out of the group. So I've been doing that for this abelian group, and I've been doing that for this non-abelian group, trying to make a picture. But here, this picture is not so good because I can't really draw it on the blackboard faithfully because the sizes start changing in order to fit it on the blackboard. So, but see, every part of the picture should be the same as every other part. Like that one over there. Every part of the picture looks the same as any other part, geometrically. So what you can do is you can define a distance between any 2 points, which is if you have any 2 points, just count the number of steps it takes to get there, and take the minimal such word that goes from here to here. Here, the word is essentially unique. But you can do dumb things. You can go like this, back up and do that. You can do that. That would have length 1, 2, 3, 4, 5. But I want to take the minimum one. And there might be, some group may have, it turns out these 2 elements commute, so you get to the same thing. So then this path and this path would be equal, or if you went like this and like this, that wouldn't be the shortest path, it would be like this. Stuff like that. So you define what's called the word length in a group, the distance, how many. So first you define the distance from the so-called identity element in the group to any other element, x. And then if you want to know the distance between, say, A and B in the group, well, what you do is you just form the element A inverse B. So this is, first you do, so this will be, if you apply this on the right to B, then this will translate this pair of elements to the identity, and the A will become the identity. Oh wait, no. Translate by A inverse. So the identity, multiply A by A inverse, that's the identity, multiply B by A inverse, and you get B A inverse here. So you define the distance between A and B to be the shortest path that, in words of generators, that go from the identity to B A inverse. Okay, now, so this defines a notion of distance. So when you have a notion of distance, you could try to make a picture where the pieces, somewhere where the distances are equal to the distances with the somewhere where you are. You might be in space or some crazy mathematical space. Now, this depends on a choice of generators. But it defines something nice. It defines a notion of distance, which by definition is translation invariant under translating by the group elements in terms of the multiplication. So it's like this picture here. We did it backwards. Here I wrote a picture, realistic picture in the plane. It turns out it had symmetries, but you could think of this as a picture of the group. And the word distance is not quite correct. It's sort of correct. In other words, because this real distance here is square root of 2 and not 2. But it turns out if you just draw this distance at any point, there's, well, have to move. It turns out this distance and the actual distance on the blackboard are related by factors that are universal and bounded. So in other words, the word length is approximately equal to the Euclidean length. Namely, 1 is less than, say, 10 times the other, and greater than 1/10 times the other. One metric is bigger than 1/10 times the other one, and less than 10 times the other one. So that's the idea of quasi the same. Imagine these numbers are getting big. So a million, a billion, but I multiply a billion by 10 or divide by 10. Not that, well, that's not big enough. But if you have 100 zeros, adding 1 0 or subtracting 1 0, that'd be multiplying or dividing by 10. That doesn't, you still have a large, 99 or 101 zeros, the distance. So for big distances, this is approximately, gives you an approximate picture. So then Gromov, the inventor of this idea, said, well, it depends on this metric, depends on the distance, but I mean, it depends on the source of generators. But if I chose another, there might be some smart way to write this with 3 generators. You can write these new generators, certain words in the G's, and then you can write the G's in terms of the H's. Each one is in terms of the H's. Well, there's a finite number of these, there's a finite number of these, a finite number of these. So if you write out the words in the G language, or write them out, 1,000 million long, words like that, and then write them out in the H language. So you can rewrite the G's in terms of the H's, you can rewrite the H's in terms of the G's. And then the total process of going between the H word description of an element and the G word description is just, again, multiplying and dividing. It's caught between 2 constants, because only finite number here, finite number, finite things is finite, and stuff like that. And so that means that every group is some kind of metric space, geometric object that you can picture somehow. Okay? So, yeah.
Can you always picture it though?
What?
Can you always picture it though? Can you always determine the places of 2 points? Or distinguish them from each other? Distinguish 2 words from each other?
I don't understand the question, sorry.
Like that's a thing I did I guess a while ago. So it is not the case that you can always.
No, it's 2 knots. I don't understand sentence with two knots. It's not the case that some, oh no, it's only 1 knot.
It is not possible
It's impossible.
to always tell 2 elements in a quotient of a
Yeah, yeah, this is a point from logic that I wasn't gonna talk about.
It's Turing undecidable. In fact, Chomsky has a.
Well, no, I wasn't, but I mean, we could talk about that at the end if you want. So what does this group of no relations really look like in the word metric? Well, at the time when I heard this Gromov idea, I actually knew, well, you could think of it as this graph, and you just have to keep branching it 3 times, but you have to be in a space which is big enough to allow you to keep them apart with the same distances. And so I was very elated when I heard this, because it means every group has a potential picture. So this one is, this group is like the plane, the Euclidean plane. If I put another z here, it would be like Euclidean free space. Up this 3 generators. And then Euclidean 4 space, if anyone's willing to try to think about that, Euclidean 5 space. So these abelian groups look like Euclidean space. Okay, so what do these other groups look like? So it turns out there is a, this geometry, Euclidean geometry, according to the name, Euclid, is very old. Euclidean geometry, right? And there's one other geometry that was very important. And this leads to trigonometry and all that. Does anyone know the other geometry that was very important in the history? What?
Spherical?
Oh, wait, he said.
Hyperbolic geometry.
No.
Riemann.
No. What?
Riemann geometry.
What?
Riemann.
No.
I think he said it though.
No.
No?
Think practically of history, like,
Projective.
what did we celebrate a few days ago? What did we celebrate?
Columbus Day.
Columbus Day. That's a hint.
Projective geometry.
What?
Projective.
What? I can't, who's talking? Oh, you?
Projective geometry.
No, I'm doing metric geometry, so projective geometry is an interesting thing. It's got a group and everything, but no, there's no distance preserved in projective geometry. How did Columbus get here? From there to here? What?
Spherical geometry.
Spherical geometry, right. I mean, navigation, British Empire, all that stuff. There had to be spherical geometry. Right, so we have, you can talk about geometry on the sphere and talk about angles and distances, and it's completely symmetric. In other words, you can rotate around any point, the sphere, you can move any point to any other point, and that's also true in Euclidean geometry. You can talk about angles and distances, and you can rotate. You can rotate the whole plane, and you can translate it. So there's a group here, the group of symmetries of the whole plane. It involves, now you have to go to the real numbers. You can have any real translation this way, and also you have rotations, which is real angle modulo 2 pi. It's a real number modulo 2 pi. So you have an interesting group of isometries, of things that preserve the geometry on the plane. Okay, but so this geometry is kind of finite. This is an unbounded infinite geometry. It's unbounded. So it turns out, I think somebody mentioned Riemann geometry. Yeah. Riemann tried to figure out, like axiomatics for general geometry. I won't go into that now, but he did that, and he, because his thesis advisor was Gauss, and Gauss had noticed that when you have a surface, it could be like the top of a mound of, like a sort of a hill, and the way it's curved is called the Gaussian curvature. It's a positive number. It could be flat like the plane, or it could be like a mountain pass, where one part is curving this way and one part is curving that way. We call this negative curvature. This is called negative Gaussian curvature. And then Riemann set up a general formulation where you could talk about these curvature ideas in all two-dimensional directions in the space. So in 3 space, you'd have 3 two-dimensional directions to talk about. And so that's called differential geometry. Turns out there's one more interesting, totally perfect, so let's go what perfect geometry means. It's every point looks like every other point, and you could rotate completely about every point. So we have this geometry, I'll call this the plus geometry, because here everything looks like positive surface of a sphere. It's like positive, like a mound. And this is zero curvature, it's flat. And there's one more geometry which looks like this in dimension 2. There's one more geometry that looks like a mountain pass. And how do we get that? So, yeah.
Is it hyperbolic geometry?
Yeah, it's good, well, yeah.
Okay.
Why do you like that word so much? Are you the one who said it before? No, you said it before. Okay. I'm going to call it non-Euclidean geometry, unbounded non-Euclidean geometry. So it turns out there's only one other unbounded geometry. Like this is unbounded, this is bounded, this is one other one, and it's unbounded, and it looks negative at every point. Now you actually know if you go out and look at certain plants and leaves, they sometimes have negative curvature, and somehow they stop, they have an edge because they can't live inside space. They can't even live inside 3 space without getting very, I've seen things grow out that there's bounding, like these hats, very floppy hats. They have a big brim, not brim, what do you call the edge of a hat? Grim? Okay. So, unfortunately, a nice way to start talking about it, I want to choose, this was actually because of Kant's philosophy in the 18th, and the strength of religion and so on. This geometry was not, I mean, some people knew about it and didn't even write about it because it would be very strange. It'd be like they're saying there is no God and stuff like that. Or Kant's philosophy was, Euclidean geometry was absolute, space is like that. So even Gauss and even Poincaré was a little bit, no, I forget, it doesn't matter. So I'm going to draw something which I'll call the light cone. So I'm going to write a formula down. See, Riemann taught us how to compute lengths in vector spaces. So this is a picture in 3 space. And what is this thing I've drawn here related to that formula?
Is the level set of that?
What?
Is it the level set of that?
Yeah,
Give me a
it's a level set where this is equal to 0. Yeah. Set this equal to 0, then you've got x plus y squared equals z squared. So if you choose a height z, well, if you choose z equals 0, x squared plus y squared equals 0, x equals y equals 0. So it looks like that point. If you go up a little bit or down a little bit, z squared is positive, either case, and then you get the circle in the xy plane of radius z. So this is the picture of solving this equation for all x, y, and z that solves this equation. Okay? Now, let me erase these now. This is just to tell you what it is. Now, who said the level sets? You?
Yeah.
Yeah. So now, let's see. So this is where it's 0. On one side is positive and one side is negative. So this separates the space into these two parts and this part. This is in 3 space now. Okay. Now, is it positive here or the negative here?
Negative.
Now look on the axis where x and y are 0. The z-axis, right? So you can see if x and y are 0, then this number is negative. So we could take a negative level, we could set this equal to -1. And by the way, it's reflection symmetry. So you get the hyperboloid, which you studied probably in high school, of 2 sheets. That's if you set it equal to -1. And if you set it equal to +1, you get something on the outside. You can see, suppose you, well, let me try to not say everything that comes to my mind. Oh. Now, here's an interesting point. This is not one of Riemann's geometries. In other words, you think of this is supposed to be, this would be the formula for the length squared of a vector. You have a vector, the x, y, and z coordinates, then this is the length, but you see this length is sometimes 0. So that's not a good notion for a geometry. It's not what we call an inner product, which the length of every non-zero vector is non-zero. Yeah. So, but now here's an interesting fact. If you think of the picture, think of the tangents. Tangents of this picture. They're all pointing out like this, right? They're all pointing out here, where this formula is positive. See, every tangent vector points out, and see, if I have to slide it to compute its length, I slide it to the origin and compute its length with this formula. But all these tangent vectors are, see, they're less than 45 degrees. This is supposed to be, I didn't draw it right. It's supposed to look like this. For 45 degrees. Anyway, it's less than this angle here. It's supposed to be at 45 degrees. So that means when you translate it to the origin and then compute this number for it, then it's going to be positive. So this is actually the way Riemann set up the geometry. He said on every tangent space, you have something like a surface, which is a 2-dimensional geometry. And on every tangent space, you have to have the notion of an inner product, giving you the length of vectors. And then you integrate those along paths to get lengths of curves, and you have geometry of curvature and stuff like that. That was Riemannian geometry. So what's interesting is that, okay, so we get this metric, I mean this notion of length. So to have a notion of geometry on a continuous space, we have to have a notion of length of curves, and we can have that if we have a way of talking about a calculus length of dx tangent to a curve, and we integrate the dx in the curve to get the length. That's a quick summary of Riemannian geometry. So this, now let's just take one of these components, take one sheet of the hyperbola, two sheets. Then the entire group of linear transformations of three space, which preserves this expression, acts on this whole space. It preserves these pictures, it preserves all the levels. If it preserves this expression, it preserves all the levels. So the entire group that preserves this expression of linear transformations, you think of 3x3 matrices and you make linear transformations of three space that preserve this expression, then it will preserve the levels. This is the level of -1, and by continuity, you know, you can flip over, but let's just look at the continuous part. So you have all of these symmetries. And the metric is defined on, the infinitesimal metric is defined using that expression. So these will be isometries. And now notice that you have spherical symmetry here. This will preserve, rotating around like that is rotating the x and y part. So you have this spherical symmetry. And then it's an exercise to prove that you can move any point on a hyperbola of one sheet to any point on the same sheet by a linear transformation of three variables. So this, you could rotate, and you can conjugate that rotation to a rotation about any other point. So this is possibly a new geometry. Maybe I've fooled you. Maybe I've written a funny representation of Euclidean geometry. I certainly have not written a funny representation of this geometry. Why? This geometry is on a non-compact, unbounded surface, this hyperboloid. So it's not a sphere, right? But it might be the plane. Yeah.
I mean, we could like draw like lines that would appear parallel on a plane and see how many we could draw. And then like we could test a parallel postulate that works for this certain geometry and see if it's different.
Okay, you might try to prove. Yeah, well, okay. Well, okay, I see, that's a very good idea. He's saying Euclidean geometry satisfies the property. Well, first I want to show it's a geometry, and then you're suggesting a way to, well, I'm in the midst of showing it's a geometry. And geometry means you have a notion of length of everything and angles. You have a full notion of geometry in every tangent plane, and then it should be totally symmetric. By rotation and translation, you get to every point and you rotate around. Well, so that's actually a very good point. So he's saying, see, Euclid had the parallel postulate. It had the notion of lines, and a point not on a line, and there's a unique line not intersecting the other point. That's the parallel line, the parallel postulate. In fact, they tried all through the Middle Ages to prove the parallel postulate until 1800s, really. They tried to prove the parallel postulate from the other axioms because it's true, because Euclidean geometry is like the only geometry. So it's true there. So they tried to prove it. Okay. So, but it turns out this is a different geometry. It's a new geometry. And it's because the group that, I don't have time to say that, but we can discuss it. It's a nice exercise that if you look at 2x2 matrices of determinant 1, then you'd be left with 3 parameters. Because there are 4 parameters here. I specify one relation, determinant 1, then we'll get rid of one of the parameters. Then there's 3 parameters left. Then, and then using the matrices of trace 0, you can give a matrix understanding of what this expression means, and you can prove that the group that preserves this transformation. So this is like, well, I won't say the argument, but use 2 by 2 matrices to find the symmetry group of this geometry. It's the things that preserve this expression under linear substitution. That's by definition this geometry. Yeah.
Yeah, since doesn't the x squared plus x squared plus y squared minus z squared not technically meet the definition of a metric?
Yes, that's a good point. It doesn't on the whole space. This is called the Minkowski geometry or Lorentzian geometry, which is what used in Einstein's. We put another variable here. This is the metric that's used in space-time to talk about general relativity. It's not a Riemannian geometry on space-time. This is not a Riemannian geometry on 3-space, but if you restrict it to this submanifold, because of this angle property, this number is always positive. So it is a regular geometry in the sense of being. Okay. That's what this argument is supposed to explain. And then you have to do some algebra with matrices to see that there's a big group of symmetries. And it's really the set of matrices of determinant 1. And it turns out that group, algebraically, that's a continuous group, as algebraically different from the symmetries of the plane. The symmetries of the plane has got this translations in it and this rotations, and that's it. It's what's called a solvable group. It's a commutative group in the kernel, and it's an extension of one commutative group by another. This is a much more elaborate group. And so that's the argument I wanted to give you. That's like, so you can say, you don't have to compute the curvature at this point. You know, it looks like positive, but that's in the Euclidean metric. So you have to use this metric to define the geometry and the curvature. But first, you have to show that, first of all, this is transitive, it's rotation, and then the group of symmetries is not the group of symmetries of the Euclidean plane. It just has completely different properties. It's a much more complicated group. And so this means there exists a third geometry. It's non-trivial in history. 1,000 years it was questioned. People, Zachary, you can read it. So there is this third geometry. So you're supposed to stop after an hour here.
Yeah, but you can continue. You can continue if you want.
You want a little bit more?
If you want, yeah.
Okay.
If you want.
I like it, but don't give me too much. So I just have this and this. Let's see. So this argument is very nice because what it shows, if you add another variable here, then you imagine the same picture, but now it's in 4 dimensions. This is the light cone. This is the metric that's used in studying general relativity, Lorentz geometry. And again, there's this hyperboloid of 2 sheets. You have these upper and lower cones. And the same argument will show this defines a metric, and then that again will not be the Euclidean geometry. So there's a third geometry. So there, in every dimension bigger than 1, there are 3 geometries: positive, 0 curvature, and negative curvature. And this picture that I was trying to draw can be drawn isometrically inside this 2-dimensional non-Euclidean geometry. You can draw this big picture. Everything is isometric. There's enough room. These geometries grow exponentially fast as you go out. And so I already knew that this geometry existed when I heard about Gromov's idea, and I said, wow, the free abelian group looks like the plane, and the free abelian group looks like the plane, and the free non-abelian group, it sort of embeds in the hyperbolic plane. So it looks kind of like the hyperbolic plane. actually, there's a nuance here, so it's not quite the hyperbolic plane, but it looks like it. So I said, oh, I can study group theory now. I don't have to be like a computer, words and substitutions and stuff. I can think. Okay. So this is just the idea of making a picture, okay? And then so we have pictures for groups. So now I want to, now this is a kind of model of this non-Euclidean geometry. So in every dimension you can make this model, but let's just stick to the two-dimensional plane now. So we could try doing your suggestion, no, yours, yeah, about trying to show the parallel posture. So it turns out in this geometry, if you draw a line and take a point on the line, it turns out there's a whole infinite family of lines passing through this point that don't intersect that. There's one that's asymptotic to this one at infinity, and one that's asymptotic this way, and then there's all the other ones, well, and then all the other ones, well, this is 2. It's hard to draw, oh, yes, one of the models of this is a finite disk like this, so they don't intersect like the right. And that's not right. Well, right, it looks like this. Anyway, there's infinitely many geodesics passing through this point which not one. But this is not a good way to proceed. So after Gromov, the next innovator, in fact, the colloquium talk today was about this word with him. Bill Thurston. His son is also a distinguished mathematician named Dylan Thurston. He was playing with hyperbolic geometry in high school. Like it's interesting. Here's something you could do if you really want to get a feeling for being. He kind of spread the idea that you should live inside the non-Euclidean geometry. You get a feel for it. Okay, live inside of it. So I'm going to tell you a couple of points about living inside of it. Okay, so let's see. So parallel postulate is not true, but I did give a good presentation, but I wanted to tell you something else first. So there's something else, there's a new kind of object that you don't have, we're not used to before. I mean, here we have equators of the geodesics, and Euclidean geometry, straight lines of the geodesics. There's something else which is very unusual. So the idea is this. So there's Austin there. Right, okay. So consider in this geometry the circle where I'm passing through me with center at Austin. Now Austin, would you go out of the room and go way back? Just go to the far wall there. No, the far wall outside the room, all the way straight, so we can still see you, some of this, okay. Now he's further away. I take the circle centered at Austin and passing through me. Now, suppose let's just pretend you're doing this, go out the door and then come back. Go out the door, go over to the Simon Center, and then, yeah, he went to the Simon Center. He went over to the Simon Center, consider the circle passing through Austin over in the Simon Center and passing through me. Now what happens if you do this in Euclidean plane? Come back, Austin.
There you are.
You did it. Okay. What happens when you do this? You send the center further and further away. Come in, Austin, come in, thank you. Tim, what happens to this circle that I'm on? It's what?
It basically starts to look like a line from
Yeah, yeah, it becomes bigger, and the curvature becomes less and less, and it becomes a straight line in the limit, when Austin is way the hell down in New York City, okay? Okay, now think about Thurston, he started making us think this way. When I mean big, I mean, go to California and draw the circle center U and passing through me in this geometry. You can do it, it's an unbounded geometry, okay? Then what happens? Turns out in non-Euclidean geometry, these circles all have curvature greater than 1. If you say curvature minus 1, if you take the standard normalization, they have curvature minus 1. The circles, no matter how far away the guy is, the curvature of this circle looks like a circle like this. Okay, but of course I'm on the radius of a big circle, a big disk, so it's getting very long. So there are these new objects. There are these new objects in the space that are called horocycles, which are kind of like circles with center on the horizon. And they're parallel. I mean, if I step forward and to draw the circle that he's going off to California, I still get a horocycle here. If I step forward, if I step back,
Somebody wrote a game about it. You don't have to describe it. You can
I
just
can't understand you. Sorry.
Somebody wrote a game in something in a hyperbolic space.
What?
Somebody wrote a video game. You can just play
Okay.
it on.
Yeah, that probably one of Thurston's early students from the 80s, maybe 70s.
It's open source.
Yeah.
You can-
So this is like a new thing, and actually, these are equidistant, they have curvature 1. These are inside any hyperbolic geometries. It's like a new thing. And usually when I used to work on this pretty much. This is the main tool to understand things. For example, this object here isometrically embeds inside this non-Euclidean geometry. There's enough room, and well, I don't want us to say that. I want to get to. I'm just going to try to. Okay, so we have, and then if we did this in 3-dimensional hyperbolic geometry, then it would be a sphere. So if I were in 3-dimensional, I'd have to send Austin off in a spaceship somewhere and say, draw the sphere with center U and passing through me, right? And again, if I look locally, it turns out these would be bigger and bigger spheres, but in the limit, Austin would be at infinity. The center would be at infinity, and this would be the sphere minus a point at infinity. Okay, well, sort of out of the way. I passed it to you. Okay, so it's a sphere, but the center, sort of only part of the sphere. When one point of the sphere disappears, the center and that point disappears. It's like this. It's like an R2, a 2-dimensional plane topologically, but it's curved in the space. And if I step forward and send you to infinity, it'd be another congruent property. So all of these, see, these are not congruent. If I draw them on the blackboard, they're not congruent. Right? This has more curvature than that one. But in hyperbolic space, they are congruent. So in high school, Thurston made hyperbolic paper, which is you cut thin strips of paper. I invite you to do this. I did this myself when I first, to get the feel of this. It uses a lot of paper. You cut circular strips, thin circular strips. Cut a lot of them, about the same radius. They're all congruent in Euclidean geometry, these circular strips. But you have to use a lot of paper because you have to go like that, and then you waste all the stuff here and the stuff here. You can't build another one. You get like 2 or 3 out of one piece of paper. And then you paste the inner edge of one to the outer edge of the other with Scotch tape. Okay, you put them together like this, okay, and you get this sort of funny thing. And then you take another bunch of paper and you build another set of these circular strips, glue them all together. And then it's amazing, you place one on top of the other. Of course, if you line them up so the strips line up, they fit. But then it turns out you could turn them. It turns, and they stick together. It's sort of remarkable. It's approximately hyperbolic space. Okay, and so this is seeing this from this picture of the horocycles. So I invite you to try that exercise. I'll round up quickly now. So not that quickly, but pretty quickly. So there's a lot to say, which I didn't say, about the three geometries on surfaces, but so at every dimension, there are exactly three totally symmetric geometries. There's the spherical geometry in every dimension, there's Euclidean geometry in every dimension, and there's the non-Euclidean unbounded geometry in every dimension, which is somebody wanted to call hyperbolic geometry. Who is that? Yeah.
No, the person who said it was.
Yeah, so someone said hyperbolic geometry. Yeah, okay, good. Yeah, so that's what it's called, hyperbolic geometry. It's also the unique, bounded, totally symmetrical geometry in dimension n. Unbounded, totally symmetric, and characterized it uniquely. It's isotropic, same in all directions, and homogeneous. Every neighborhood or every point looks congruent to every other neighborhood. Okay, so there's three of those in dimension 2, and then, so the question, so I just wanted to, and I'm going to use the whole lecture to make this a fast description. So there's a theorem that Thurston formulated around 1980, and it was proven largely by him, sort of generically. But the statement in that period, but the statement included one of these millennium problems, the Poincare conjecture, and this was funny. But he was proving some of the other parts of the statement. I didn't say the statement yet. And then eventually people in partial differential equations started working on it, and they sort of recovered what he had done and then proved the whole thing using partial differential equations. Okay, but so it turns out, suppose we want to study these abstract, see, what's very beautiful is in 2 dimensions, there are these 3 geometries, plus, 0, and minus. These 3 geometries. And it turns out that in a certain sense, every geometry in dimension 2, if you rescale the geometry pointwise by a varying scaling factor, can be made in a canonical way, can be made to look like one of these 3 geometries. So let me just say that. These 3 geometries are amazing in what they do about all Riemannian surfaces. So you have to rescale the Riemannian geometry, possibly, but then like a banana or a gourd, you draw curves on it and see their angles. I rescale the geometry of the gourd, and then it's equal to the round sphere. You can rescale, and any kind of pretzel, any kind of donut, you can rescale this geometry to look like Euclidean geometry. And it's a surface with like a pretzel with lots of holes. Any geometry you put on that, you can rescale it to make it look like hyperbolic geometry. Okay. So I don't have time to discuss that, but that's, so it's very important. And that was known already around 1900. It was Gauss and Riemann had laid the groundwork for it earlier, and then it's completely general. Whether the surface is infinite, crazy things, they're all are contained, they all can be geometrized in a canonical way, preserving the angle structure to use these three geometries. Well, that's not quite possible in dimension 3D, but there are, do 3D like this. So Thurston found 8 geometries. So 3 of them are plus, 0, and minus. Now you use these 3 geometries, so we've just begun here. 3 of them are, just take these geometries and just add like a time dimension. Think of adding time to the surface geometry. Add another dimension, something else is happening, a z-axis, add a z-axis. And you can still translate up and down, and you can still move around. So these are still homogeneous, but now not all the directions are the same, but they're still homogeneous. So take any one of these 3 geometries, which is everything symmetrical, and just add another direction. Then still homogeneous, namely now this new 3-dimensional space that can move from any point to any other point. I translate in the time direction on one surface, any 2 points to be on the same surface. I translate one so they're on the same surface, and then I move on the surface to move them together. But I can rotate in 2 directions, but I can't rotate the 2 directions into a third. So it's not quite totally symmetric, and it couldn't be unless it were one of these 3, anyway. But it's homogeneous. Every neighborhood of every point looks the same, but not the same in all directions. This time direction is different. And then there's a non-trivial way to add a 3rd dimension. There's a twisted way. So this is called Cartesian product way. You just add a time direction. But then this is Cartesian way. And then there's another way called the twisted way. Let me do Euclidean first. So there's some geometry here that's a twisted adding another dimension. So it's going to be an unbounded geometry. And the way I'm going to tell it to you is approximately, I'm going to tell you a group that looks like this geometry. Exactly. Then we know what groups look like. You have a group, you put the word metric on it, and you get a geometry. And the group is 3 by 3 matrices that are upper triangular, and they have integers n, m, and l. This group of matrices is closed under multiplication, and there's inverses. So it's a group. The twisted version of Euclidean geometry in dimension 2, twisted, I haven't said what this is, but believe me, there's a uniform way to say it in terms of differential geometry, which, when you're grad students, I can tell you it. And then the twisted one here, I'm going to give you a picture. This is, you actually take the sphere and you add another direction, you add another dimension by consider all of the directions at any point of the sphere. So this is like putting over every point of the sphere kind of like a circle. You can imagine unwrapping the circle to get a real line. Somehow, when all these little circles on the sphere of all directions, they make a 3-dimensional space. You have a 2-dimensional space, and you add another parameter. I give a point on the sphere and a direction. So that's the three-dimensional, that's the three parameters. That will actually be the geometry like the three-sphere. Locally, this will look like the three-sphere. So that's one of the geometries. And then what's this twisted one? Well, again, I'm going to, I didn't do my n-gon thing. Yeah. Well, I'll just say it like this. So I've told you that by some reason, every surface, here's an example of a surface that carries one of these non-Euclidean geometries. Locally, it looks like non-Euclidean geometry, and if you can think of this as being like, you can construct a hexagon, an equilateral, this is not quite equilateral, with right angles here. Construct this thing in non-Euclidean geometry, and then you can start reflecting it around. And then you get some tiling of the non-Euclidean geometry and the symmetries of this tiling. If you identify various points by the symmetries, then you get this surface here. And that's how you get a surface like this with the non-Euclidean geometry. And then I'm adding another dimension by having a direction on that. Turns out the group of this geometry turns out to be the same. Well, that's not important now either. Okay. Well, that's already 6. This is like a description with 2 methods of, this one uses covering spaces, this one just uses a picture, but it gives you the 3-sphere geometry. This picture could be related to this covering space, and then you have circles, directions in the non-Euclidean geometry. Yes, I could have said it that way. Yeah, I could have said it that way. Just put the non-Euclidean geometry here. So I'll just draw that, and then put the direction to make it a third dimension. So this is a homogeneous geometry. This is 6. This is 3. A 3-dimensional geometry is homogeneous. This is another 3. And then we have, I said there are 8. We need 2 more. Do we know any more? Anyone's allowed to answer. Austin.
I don't know how they're obtained.
You don't know the other one? What? Okay, you.
Maybe, alright, this is gonna sound like a weird idea, but like twist the twisted ones.
Oh, no, it's more obvious. See, none of these are, if you take the flat geometry here and add a time direction, you get Euclidean geometry in dimension 3. It's just the third coordinate. I have x, y, and z. Wait just a second. So here I get the Euclidean. And if I twist the spherical geometry, I get the 3-sphere geometry, I said. So this is 3-sphere geometry in dimension. This is the plus one. This is the Euclidean geometry, just with the Cartesian way of adding the third direction. This is the twisted way. What about that goodie? The great one, the one that's totally symmetric and unbounded. See, none of these are totally, except this one by coincidence, is totally symmetric. It's homogeneous point-wise, but not in direction-wise. There's one case here for some reason came out okay. And this one, turns out, might have been the hyperbolic one, but it's not. There's also the hyperbolic one, H3. So now this is 6, and then there's 2 more. So one of them is non-Euclidean geometry in dimension 3, which has horospheres and stuff like that. You know, it has all this stuff I said. And there's one more. I'm going to tell you what the group is. I'm going to tell you a group that represents this geometry. This has a name. It's called solve geometry. It's related to computer programming. Or some of you are interested in computer programming. So this solve geometry, you have to look up Thurston's notes and some remarks about it. Anyway, so here's an interesting 2 by 2 matrix, 2, 1, 1, 1. What's the determinant of that? 1. Determinant's 1. So this is an invertible matrix. So it acts on the group Z plus V, which is like the plane. The group that looks like the plane, the 2 by 2 matrix, looks like that. So what you do is you take this group here and you add another element. So here you have A and B, and you add another element C. Hello? Oh, I just hung up on my wife. She wants it. You got another element C, and when you move this C across an A and a B, which commute. So A and B commute in this group. And when you, C does not commute with A and B, but if you move it across a letter in this space here, you think of the B is like the vector 0, 1, and A is, this is like B, the vector 0, 1, and A is like the vector 1, 0, right? So A is this vector, which is 0, 1, 0, and B is this vector, which is 1, 0. Then when you move C across either A or B, you hit this vector with that matrix. And that gives you another vector. Now it's got 2 components, but it'll be in the group Z plus C. So that's a presentation of a certain group. It's made of 3 letters. The first 2 letters commute. The third letter, when you commute it past one of the others, you hit the matrix. This matrix, C is like this matrix, you might say. It acts on the A and B as this matrix. When you move it across, you have to act on the vector. Yeah.
Is that a semi-direct product?
Yeah, that's the name. Yeah, this is called the twisted. This is like a very twisted product. There are many kinds of twisteds. This is one kind, and this is another kind. But this is a twisted product, right? That's good. It's denoted like cross with a little thing like that. So this is Z plus Z, maybe cross Z, with a little thing under, and this little thing here means you say how this guy acts on this space by this matrix. And you move it across any vector in this space. You have to rotate the vector by this matrix. But this matrix is subtle. It's got the eigenvalues, the golden numbers, and there are 2 irrational directions, and the orbits of this action, you have like a point, and it goes along these hyperbolas if you iterate it. And so this stretches by 1.6 in this direction and contracts by 0.6 in this direction, golden numbers. And it's really super canonical group. It also has exponential growth, like the free group on 2 generators. It grows like the golden number, 1.6 to the nth power. But it's a group, so it has a picture. And this geometry, this 8th geometry is that geometry. So those, and then the theorem, the famous geometrization theorem is that every 3 manifold, I used a word I didn't want to use. Every closed bounded space, suppose you have a 3-dimensional space that's bounded. In other words, everywhere it looks like 3 space, but it's totally bounded. It has no boundary. You can't imagine it inside our space. You can't draw such a thing. You can just imagine it though. Like you take the cube and identify opposite sides of the cube. When you leave the cube, you enter on the other side. That's probably a good video game. So you just imagine abstract 3-dimensional space. It turns out I was kind of astonished when I went to grad school to find out that studying these objects, I'm in my last sentence. Be home soon. Who am I? She doesn't know me. Okay. Bye. Okay. Anyway. Okay. It's a fantastic theorem. It turns out every closed three-dimensional space can be canonically broken down. It either has one of these 8 geometries. It's folded up. You take this geometry and you fold it up in some way to get this bounded space, which is locally homogeneous. Or it can be, there are sort of flat torus walls in it, and there's a canonical, and then in the complement of these walls, it's either this geometry or this geometry. So every three manifold, there's 3 ors, there's 2 ors here. Every 3 manifold is either has one of these pure geometries, or it can be canonically decomposed. In other words, the way is canonical, and then each component of the complement has one of these pure geometries, and you fit them together by a very specific procedure with 2x2 matrices. And then finally, there's one more or. Remember this picture. Just think of this picture again, and think what happens when you make this level set. You take it down to 0 from -1 before, so bring it down to 0, and then this level set becomes equal to this cone at 0, and then let it pass through 0 and become positive, and then it becomes a hyperboloid one sheet that looks like this. So see, what you've done is you have 2 surfaces that come together and kiss, and then they open up into a little tube. See, these 2 surfaces come together, they kiss there, and then they open up. You know, right here, there's like a little cylinder between them. Okay, that's called the connected sum. So every 3-dimensional closed bounded space is a connected sum of pieces, and this is due to Milner to get the precise statement, Professor upstairs. And these pieces, which can't be divided into connected sums, are called primes, and the set of primes is unique. Each prime is either one of these pure primes made of these 8 geometries, or there are these walls, and there's some graph that's canonical, and then the vertices of the graph are labeled hyperbolic, or these are called cipher vibrations, and either H or S vertices, and then pure geometries are put there and they're glued together in the last one. So, and that was proven in 2005, and it included the proof just the manifolds with finite fundamental group carry this geometry. That follows from the proof. And then the generic manifold is usually like this, but then you have all the others. So, now a very interesting question is, this was already proven almost 20 years ago. It means that our space that we live in has this remarkable property. There's no theorem like this in dimension 4. There's some goody theorems, but nothing this devastating. Like already in dimension 2, it's quite devastating. Every surface has one of these 3 geometries. This is a more complicated statement involving 8 geometries. So this has to have great significance for reality. Our reality is in 3 dimensions, and there's this fantastic result about it. So I think there's a whole research problem. Why are 3-dimensional spaces the way that they are? There's 8 geometries. So for the next generation, you tell me. Send a telegram to somewhere. Okay, that's it.
Yeah.